Try this for a second. Picture the coldest place you can possibly imagine. Most people's brains go straight to outer space, that vast, empty, sunless void between stars, where there's nothing around to keep you warm and nothing to stop the cold from just going on forever. Makes sense, right? Except it's wrong. Dead wrong, actually. The coldest known place in the entire observable universe isn't floating somewhere between galaxies. It's sitting inside a laboratory on Earth built by actual humans, and it is colder than anywhere else we've ever detected, anywhere in the whole cosmos. I'm Potato, and this is Potato Science, where today we're chasing cold all the way down to its absolute limit and figuring out why the emptiest, most desolate regions of space still can't beat what a handful of physicists managed to pull off right here at home. Stick this one on repeat if it's messing with your head as much as it messed with mine, and toss a subscribe our way while you're at it, because there's plenty more of this brain-bending stuff coming. Now onward. Let's start with space itself, because the assumption that it's the coldest possible place isn't a crazy one. Space really is cold, unbelievably cold by everyday standards. But it's not actually as cold as most people assume, and it's definitely not empty in the way that phrase suggests. Even in the deep, seemingly vacant stretches between galaxies, there's a faint, uniform glow of leftover heat left over from the Big Bang itself, called the cosmic microwave background radiation. This ancient afterglow keeps the average temperature of deep space hovering around -270 degrees Celsius, or about 2.7 degrees above what scientists call absolute zero. That number, 2.7 degrees above absolute zero, is the baseline temperature of the universe almost everywhere you go, whether you're near a distant galaxy or floating in the emptiest patch of nothing scientists have ever mapped. It's remarkably consistent, this faint cosmic warmth left behind from an explosion that happened almost 14 billion years ago, still gently radiating through everything, refusing to let the universe cool down any further on its own. So if space itself sits at around 2.7 degrees above absolute zero, and can't get any colder without some outside intervention, where does a colder temperature actually come from? This is where human engineering enters the picture, and where things get genuinely strange. In laboratories here on Earth, physicists have developed techniques capable of cooling small amounts of matter down to temperatures that make deep space look downright toasty by comparison. The record holders for the coldest artificially created temperatures have reached fractions of a billionth of a degree above absolute zero, so close to that theoretical floor that the numbers stop being intuitively meaningful to most people. We're talking temperatures measured in nanokelvins, a scale so extreme it barely resembles anything in ordinary human experience. One of the most famous methods used to reach these temperatures involves something called laser cooling, which sounds like it should make things hotter, since lasers are usually associated with burning or heating, but does the exact opposite under the right conditions. Here's the basic idea, and it's honestly one of the cleverer tricks in modern physics. Temperature, at the most fundamental level, is really just a measurement of how fast particles are jiggling around, vibrating, moving, colliding with each other. Hot things have fast-moving, energetic particles. Cold things have slow, sluggish, barely moving particles. Absolute zero, in theory, would be the point where particles stop moving entirely, the coldest anything could possibly get, because there's simply no motion left to remove. Laser cooling works by carefully aiming lasers at atoms in such a precise way that every time an atom absorbs a photon of light, it gets a tiny nudge that slows it down slightly, specifically because the laser frequency is tuned to interact with atoms moving toward it, effectively acting like a very targeted, very gentle braking system at the atomic scale. Do this enough times, with enough precision, using multiple lasers pointed from different directions, and you can slow atoms down dramatically, draining away their kinetic energy step by tiny step, which is exactly what a drop in temperature actually means at the particle level. Combine laser cooling with other advanced techniques, like magnetic trapping and evaporative cooling, where researchers essentially let the most energetic, hottest particles escape a contained cloud of atoms while keeping the coldest ones trapped. Similar conceptually to how a cup of coffee cools faster when steam escapes carrying heat away with it, and you can push temperatures down to levels that simply don't occur naturally anywhere we've ever observed in the universe. Not near black holes, not in the emptiest voids between galaxies, nowhere. The coldest known temperatures anywhere, as far as we can tell, exist inside human-built laboratory equipment. This naturally raises an obvious question. If we can get this close to absolute zero, why can't we just keep going and actually reach it? Why does it seem like absolute zero functions as some kind of finish line that's always approached but never quite crossed? The answer lies in something called the third law of thermodynamics, a genuinely fundamental rule of physics stating that reaching absolute zero exactly would require an infinite number of steps, or infinite time, or both, making it fundamentally unreachable in any real, practical sense, no matter how sophisticated the cooling technology becomes. It's not simply a matter of engineering not being advanced enough yet, the way we might eventually build a faster rocket or a more powerful telescope. Absolute zero appears to be a genuine, built-in boundary of physical reality itself, similar in spirit to how nothing with mass can quite reach the speed of light, no matter how much energy you throw at accelerating it. There's also a deeper quantum mechanical reason lurking underneath all this. Even at the most extreme cooling limit scientists have achieved, particles still retain a tiny, irreducible amount of motion called zero-point energy, a strange consequence of quantum mechanics which essentially guarantees that particles can never be perfectly, completely still, not even in principle. There's always some minimal, unavoidable jitter baked into the fabric of reality at the smallest scales, which means true absolute zero may not just be practically unreachable, it may be theoretically impossible in any universe governed by the rules of quantum mechanics as we currently understand them. So here's where this all lands. The coldest place in the known universe isn't some remote, forgotten corner of deep space, untouched by starlight and drifting in eternal darkness. It's a carefully engineered pocket of laboratory equipment, built by scientists chasing an unreachable theoretical limit, using nothing but light, magnetism, and extraordinarily precise control over individual atoms to create conditions colder than literally anywhere else that has ever been measured across the entire observable cosmos. Somewhere out there, black holes are swallowing entire stars. Somewhere else, galaxies are colliding in slow, silent motion across unimaginable distances. And yet, right here on our own comparatively tiny, unremarkable planet, inside a room that probably isn't even all that large, humans have managed to create conditions more extreme, in their own specific way, than almost anything nature has managed to produce naturally anywhere in 14 billion years of cosmic history. There's something genuinely humbling and kind of delightful about that. We didn't need to travel anywhere. We didn't need some cosmic phenomenon to hand it to us. We just built the machinery ourselves, right here, and quietly broke a temperature record the entire rest of the universe couldn't manage on its own. That's it for this one. If chasing absolute zero down this particular rabbit hole scratched an itch, there's more where that came from, so stick around for whatever strange corner of physics we end up poking at next. See you then.